Welcome to qnawire.
In this question, we are basically looking at how we can model a free electron in a crystal lattice using Bohr's model, right? Using Bohr's model, which is supposedly for an electron orbiting around a nuclei, right? But right now, we are considering a free electron orbiting or being surrounded by a crystal lattice. Right, so this electron is free, but is kind of affected by all these nuclei, similar to in a hydrogen atom. So how can we model it using Bohr's model? And there's two key components in this. To make the Bohr model work for this particular instance, the first is that the Coulomb interaction is weakened due to the surrounding nuclei, right? So the other nuclei will reduce the Coulomb interaction or Coulomb attraction by any nuclei by a factor called kappa. So basically the attraction force initially is just Ke times E squared over R squared. Right now, because it is reduced, there's a factor of kappa introduced. And the other component would be that the mass of the electron is now, because of the interactions, can be substituted as an effective mass, m star. Right, so due to the influence of the potential of the other nuclei as well, right? It's described in the question. So what we have to do to make the Bohr model work? Well, we see that we can just replace our constant Ke with Ke over kappa, and we just replace our mass of the electron with the effective mass, m star. Now for the first part, we want to find the radii or the radius, and in the Bohr model, the radius for the hydrogen atom is just h bar square over meke times E square. To convert it into our crystal lattice kind of model, the new radii, we just replace Ke with Ke over kappa and Me with m star. So this kappa times h bar square divided by m star times Ke E square. Now we want to find it in terms of the original Bohr radius A0, so we multiply by factor of Me, right? We multiply Me in both the numerator and denominator, and we see that this is the Bohr's radius, and this is our additional factor on the left. Right, so there's just kappa times Me over m star times the Bohr radius. Now to substitute in numerical values to evaluate this expression. So we are given the effective mass is now 0.22 times of the electron mass, and then we multiply this by kappa, which is given as 11.7, and of course the Bohr's radius, which is 0.0529 nanometers. We should get about 2.81 nanometers. So it is actually a lot larger than the Bohr radius. Next, we move on to the energies, right? So the energy levels. So for a typical hydrogen atom, energy level is described as negative Ke E square over 2 A naught times 1 over n square. So we do the same process. We substitute in our Ke to become Ke over kappa, and since we already substituted A naught, right, and we show that A naught becomes A prime, so we can just substitute in A prime below for the A naught. So this is Ke square over 2 kappa times A prime times n square, and we know that A prime is me over m star times kappa times A naught. Right, so this is the expression that we have, and in terms of the original Bohr radius, so this is the modified one. Let me just call this En prime. So in terms of the original En, well, we can try to separate it out as such, right? We have this part, which is the original En, of course including the factor 2 inside. So this is actually negative m star over me times kappa square times the original energy levels for the hydrogen atom, En. And now to substitute in the values, right, numerical values for the first, or for the ground state electron, that is n equals to 1. We know that the E1 ground state energy for hydrogen is 13.6 eV. So we get so there shouldn't be any negative sign over here, right, because the negative signs get taken up by the En. So what we have here, the original ground state energy should be negative 13.6 eV, right? Sorry for the confusion. And putting that into the expression, right, we already found m star over me, which is 0.220 divided by kappa square, which is 11.7 square, multiplied by E1, which is negative 13.6 eV. We get about negative 0.0219 eV.